Okay, can you hear me?
Yes. Okay, great. So we're going to start.
Can you hear me? Well,
yes, we can hear you. Okay, great. Okay, so we're going to now have three short presentations by Glenn, Laura, and David. And then afterwards have informal broad discussion. And one other thing, I understand that Mark has to leave in about an hour. So if you have questions for his talk, maybe raise your hand immediately after the panel presentations are over so that gets a chance to answer them. Okay, but now let's start with the panel presentations. The first one is by Glenn Barnich from Université Libre de Bruxelles and Solvay Institutes, and he will tell us about gravity with boundary conditions from asymptotic symmetries to discrete dualities.
Okay, thank you, Andrea. Thanks to all the organizers for the opportunity to participate. So you know that in full general relativity, there is no global symmetries. So there's no co-dimension one Noether charges. And if you're interested in full GR, you can also show that there's no surface charges which are conserved on all solutions of the equations of motion either. So if you want meaningful questions, you have to begin to talk about fall-off conditions, how you approach some flat backgrounds. You need some kind of linearizations, even though we heard that the nonlinear terms are also very important, of course. But nevertheless, in order to set up the problem, this is the kind of things that you need. So when you think about asymptotic symmetries, of course, this has to do with the boundary being at null infinity or at spatial infinity. But then the next natural question is to have boundaries at finite distance, for instance, and then you have to begin to think about boxes with boundary conditions. And really what you are then studying is finite size effects engaged in gravitational theory. So how do they depend on the boxes that you put and also on the boundary conditions that you put in this box? So what are good boundary conditions is a very tough question that infinity, as we heard, you do consistency guides what you are trying to do, but at finite distance, it's very hard to find natural ones and or to find physically motivated boundary conditions. And some that I like particularly is the ones that, as Bryce DeWitt puts it only in his 1975 physics report, is so he's trying to understand what boundary conditions to put on a scalar field by all means. And he's saying, okay, Dirichlet conditions are natural, but are they good ones? And then he's saying that in electromagnetic theory, we know a perfectly good set of boundary conditions, and these are perfectly conducting boundary conditions. These are the ones that you learn in your undergraduate courses, which tells you that if you put two perfectly conducting plates, parallel plates, that's the situation, but it can be more general, then the longitudinal part of the electric field has to be 0 and the organelle of the magnetic field has to be 0 on the plate. So they are really physically motivated from the interaction of the electromagnetic field with the electrons in the plates, if you will. Okay. So you even have a kind of microscopic understanding why you impose those and not others. Okay, but of course it's a kind of approximation nevertheless, but I'm going to study electromagnetism or linearized gravity in what I would like to call a Casimir box. And this is, you have two large transverse direction, then you have the plates sitting at x3 is equal to 0, x3 is equal to d. And of course, if you think about space-time, then you also have the thermal circle, and you know that you have periodic boundary conditions in Euclidean time. So then, with a lot of work, you can actually prove that the partition function for this system is in fact exactly the same than the partition function of a massless scalar field with periodic boundary condition, where instead of having this interval here, you have another circle, which is the spatial circle in this time. So you really have a torus plus times some large spatial direction, and L3 for this equivalence to work has to be twice the distance of the plate. So you don't need to study any longer electromagnetism or linearized gravity, you have done all the kinematics, and you just reduce to partition functions for scalar fields with periodic bound conditions on this space-time. Okay, and so one observable that you might want to study, but of course you can study more general observables, is the partition function, and you couple the linear momentum in the compact direction, because then you can define this modular parameter, which is really defined by the imaginary part is beta over LD, the length of the spatial cycle, and the real part is related to this chemical potential that we put. And you can compute this partition function. It's actually, of course, an exercise in free field theory. In D is equal to 1, of course, you find the famous conformal field theory result, where it is given, where it is holomorphically factorized, and it's given in terms of the Dedekind data function. And the zero mode, a particle, is giving this 1 over square root of tau 2, which is the one which makes modular invariance work, in fact. In higher dimensions, you can do the same computation. And like Prahar, for philosophical reasons, but also because one can, I'm just doing it in any spatial dimensions, d minus 1, and not necessarily d is equal to 3, because you can really study what depends on the dimension. So you find that the result is proportional to the volume of the transverse dimension times something which makes this adimensional. And then there is what is called the real analytic Eisenstein series, which it's no longer holomorphically factorized, but the nice thing of this expression here is that you know its modular properties. So it's in fact, the partition function then is modular covariant, and it's only for d is equal to 1 that it's really invariant. But everything is known about these partition functions, in fact. And what is very nice is that if you do canonical quantization, you find the Fourier expansion of this Eisenstein series. If you do zeta function method, you find the series I have just given. But if you do, for instance, world line methods, so really heat kernel world methods, you really find the Mellin transform of this partition function. So really the same kind of things that you see in celestial amplitudes. So the low temperature expansion, of course, you can work it out, and there is then the Casimir energy of the system, which if you want, you can write in terms of a central charge, which is the central charge for this massless scalar in this geometry, and it's given in terms of basically the zeta function and then something which makes it adimensional. And then you can, of course, also work out the high temperature approximation, and it's really the scalar black body result. Again, write it out with PD if you want to make these Cardi formulas work in these higher dimensional settings. But one thing that I find particularly striking is that if you look at the full low temperature expansion that you get from the operator approach, so the leading piece, as we discussed, is just linear in beta with the Casimir energy. There is a subleading piece which is also polynomial in beta, and which goes like the black body result for a massless scalar in d minus 1 dimension. And then you have all these exponentially suppressed terms in terms of modified Bessel functions that we also have seen in previous talks. So they are all exponentially suppressed at low temperature. And then what is kind of interesting, and I still have not understood if it's really deep or trivial, is that at least for this geometry that I've been considering, the leading contribution to the entropy, if you're not doing the usual thing and looking at high temperature in large boxes, but if you look at low temperature in a small box, it really scales like the area of the plates. And you can understand this in terms of microstates. So contrary to what I have always been thinking, it has nothing to do with soft degrees of freedom. I really should say it is belonging to the hard part. But nevertheless, you can completely understand it in terms of photons and gravitons. And you realize that this contribution, the leading contribution to the entropy, really comes from photons or gravitons that propagate parallel to the plates. So you can see that because the N3 is really equal to 0, so the angular frequency. Okay, maybe one more comment of general nature is that, of course, you have put the system in the box, so it's infrared regulated completely, except for some zero modes, some particles which are there, and they are responsible for that you have to put sometimes primes, and you cannot sum over all of these discrete numbers. So it's really infrared regulated. That's one thing, and you really understand everything in terms of Feynman diagrams. Of course, this is just a one loop Feynman diagram, but suppose you do finite temperature field theory and you do perturbation theory. So you can also work out not the partition function, but the thermal 2-point function. And you know from this nice paper by Jarkif and temperature field theory, it's only the 2-point function that is really sensitive to the boundary conditions. All the rest, the standard perturbation theory, just goes through as usual, if you want. So you have this thermal 2-point function in terms of a Mellin transform, and you see it in terms of a Riemann theta function. And you can really study some limits as you want, that you have complete control. Okay, let me stop here.
Thanks a lot, Glenn. Let's continue with the second speaker. Laura, can you share your screen?
Yes. Can you hear me?
Yes.
Okay. All right.
Okay, our second speaker in the panel is Laura Donnay from TU Vienna, and she will tell us about BMS flux algebra and celestial holography.
Thank you. Let me start by thanking Andrea, Agnese, Angelos, and Stefan for organizing this very interesting workshop. So yeah, I will present this in 10 minutes, the results that we got recently with Romero Zicconi about BMS fluxes. So our starting point in this work was the usual gravitational solution space for assembling flat space-time in Bondi gauge. So as you all know, we have the Bondi mass aspect, the angular momentum aspect, and the gravitational shear, CAB. And Q naught here denotes the unit round sphere for the celestial on the celestial sphere. And I will consider the so-called extended BMS symmetries. Namely, I will consider the super translation symmetry spanned by this function curly T in my notations, and the original proposal by Glenn and Cedric, namely the super rotations are taken to be local conformal vector on the sphere, which violate the Bondi fall-off at isolated points. And of course, we have our known BMS4 algebra. So let me briefly comment on this NAB VAC story that Alok and Campiglia already explained earlier today. So we know how the bulk superrotation act on the functions, and superrotations transform, induce a inhomogeneous transformation on the news. And this led Geoffrey, Adrien, and Romain to introduce the so-called shifted news tensor and hat here, which is defined as the time derivative of the shear minus this vacuum tensor NAB vac, which can be related to the so-called Liouville or super boost field. So this phi here, you can see it as labeling the super rotation vacuum, and this NAB vac is related to the stress tensor for this sort of 2D Euclidean Liouville theory, where phi is the Liouville field. So with that, the transformation law of this Liouville field is such that now this shifted news tensor transform in a homogeneous way under the action of the extended BMS symmetries. And an important aspect of that is that any radiative configuration has a vanishing shifted news tensor. one can impose, it's actually important to consider the following fall-off conditions at the boundary of null infinity that were also advocated by Miguel and Alok in their recent paper. So of course, associated to this shifted news, you have a shifted shear, and this is, I'm using the same notation I think as Miguel, but this was called C by Alok earlier today. So we have the following fall-off conditions at the boundary of scribe plus for the shifted shear, where C plus is the value of the super translation field as scribe plus plus, and C minus the value as scribe plus minus. So this U fall-off condition implies that the shifted news is 0 at the corners of future null infinity, and that this shifted shear is purely electric. So this is the electric conditions. So importantly, these quantities were used by this author to prescribe a well-defined Hamiltonian that close an algebra at the corners of scribe plus. So here I want to stress that the bracket here is the usual Lie bracket. It's not the modified Lie bracket of Glenn-Cedric. And there is no central extension or Tuco cycle in this relation. So there were a similar result obtained by Miguel and Javier. So this means that the generalized BMS for algebra is realized also at a spatial infinity, and we heard about that by also from different perspective from Mark's talk. So I will want to define what I will call the BMS fluxes and tell you that they can be seen as conformal primaries on the celestial Riemann surface. So here, what I will consider, I want to stress that I will consider Vera-Zero primaries. So this is the usual, of course, action of Vera-Zero on the primary field of weights H and H bar. So the first object that I want to discuss is the so-called supermomentum flux curly P here, which is the integral over the retarded time of the time derivative of this curly M, which is the supermomentum, which was where we use importantly the prescription developed by Geoffrey Adrien Romain, namely this curly M here involves the Bondi mass aspect plus these new contributions here, which are actually crucial if you want the algebra to close at the corners of Scri. So now using the phase space infinitesimal transformations on this function, you can actually see explicitly that this curly P transforms as a primary fields of weights 3/2, 3/2. One can extract out of it a soft part of it, which can be rewritten in terms of the leading soft operator N0, which is a 3/2 minus a half, using this super rotation covariant derivative curly D here, which was also considered in these papers. The second object is the superangular momentum flux curly J, which is now given by the boundary values of the superangular momentum curly N, which again involves not only the angular momentum aspect, but this kind of involved expression, again, importantly, including the presence of this N and vac, this vacuum news tensor. So this object transforms as a primary field of weights 1,2, and there is a complex conjugate of this object, which is a 2,1. Again, one can prescribe a good soft part of this object that is related to now the subleading soft mode, and which also importantly involves actually the super translation field. I think Alok pointed out also something very similar. So this big F is the total flux. It's actually the pairing between the BMS generator here in orange and the momenta that I just presented, curly P, curly J, and curly J bar. And using this pairing, one can then interpret the transformation laws that I have shown before as the coadjoint representation of BMS4, which was worked out in details in a recent paper by Glenn and Romain. So this is where these transformation laws appear. Now one can again define a soft and a hard sector of this flux involving the soft part of the superangular momentum fluxes and super momentum fluxes, and in such a way that the soft part also transforms in the coadjoint representation. So this is a summary of the different ways for different objects. So these are the BMS symmetry parameter, super translation, super rotations, and the fluxes that I have presented. This is the leading soft operator, and this is the subleading one. So in this work, we constructed these fluxes with a prescription, which was based on earlier work of Compere and Romain and Adrien, which is such that these fluxes vanish for non-radiative solutions, and the U-fall of condition make them finite. They are some U-integrated expression of the gravity solution space that transform in the coadjoint representation of the extended BMS group, and the inclusion precisely of super rotations involve a careful treatment of this vacuum structure via the Liouville field. So in the paper, we also discussed how these objects are related to the CCFT currents, namely more precisely how this curly P is related via this curly derivative to the super translation current, and similarly how this curly J can be related to the 2,0, so the stress tensor of the celestial CFT. And we also computed the algebra by these fluxes and show, so they close with the standard bracket, and from that you can actually very nicely deduce the OPEs of the CCFT from these BMS fluxes. So I'm done. Thank you very much.
Thank you, Laura. And now next talk is by David.
Yes, let me share my screen.
Yes, please.
Sorry, 1 second. I'm on a new computer.
Okay, I think we lost David. Okay, until he comes back, are there maybe any questions for Mark, since he has to leave in a bit?
Oops. Yeah, sorry about that.
Just back. Sorry, Mark,
yeah.
Let's leave questions for afterwards.
It just crashed, but I'm hoping you can make me a co-host again, and I hope this will work now.
Yes, until making pause.
Okay. Okay, sorry about that delay on a new computer here. So there's some hang-ups, but anyway, Thank you very much for the invitation to talk at this Celestial Amplitudes workshop. I'd actually like to change gear a little bit and discuss some astrophysics. So let me go back. So I think for this audience, I don't need to give so much motivation for why studying the infrared structure of gravity and gauge theories is interesting. And I'll focus more on the second point of the observation that you may not be aware, but there's actually a good chance of being able to at least access the gravitational wave memory side of these infrared triangles that I've mentioned above. And to be a little more concrete, within this decade, I think we will be able to measure the gravitational wave memory effect, and we'll be able to study it precisely within the following decade. So this, I think, is quite interesting, that this is going to become an observational field relatively soon. Okay, so what then are the observations that one can make? They involve these three detectors that you've likely heard of, the two LIGO detectors in the US and Virgo detector in Italy. And very soon a fourth player will enter the gravitational wave detector game, and that's the Cogra detector. And these Michelson interferometers, they essentially measure very small changes in the arm lengths or very tiny strains. So if you imagine that these detectors have equal arm lengths, initially there would be no light coming out of the interferometer. But when a gravitational wave impinges from the top, it causes some light to leak out, as illustrated in this movie. And this can be calibrated to a strain. Since these are kilometer scale detectors and extremely sensitive experiments, the kinds of strains that we're talking about are of order 10 to the minus 23, or in physical units about 10 to the minus 19 meters. But what's crucial for detecting the memory effect is that you'll notice in this figure there's a finite bandwidth. So these detectors are only sensitive from around 10 hertz to a few thousand hertz. So this will present a challenge for the memory, for detecting the memory, but it's one that can be overcome. So if these are the detectors, then what are the sources that are most promising for the memory effect? And there, what have been detected most prominently are these binary black holes. So each triple three dots here in this image shows the two masses of the binary black hole system before merger, and then it runs into a larger mass object, the third blue dot, which is the final mass. So the scale here is just the mass in solar masses of these black holes. And then the horizontal scale doesn't have any meaning. It's just spread out so you can see all the black holes. And what I would like to illustrate is that if you go from the first observing run, where there were 3 binary black holes detected in 3 months, the second, where it sort of ramped up to 7 and 9 months, as these detectors have improved and improved, we're now in a situation where LIGO and Virgo are detecting tens and getting close to hundreds of binary black holes in a year. So there's a lot of sources that will be detected in the future. Okay, so now let me say a little bit more about why binary black holes are interesting for the memory. And to do this, I'm showing this plot of gravitational wave luminosity versus basically the separation of the binary A in units of the gravitational radius. So in other words, as you get closer objects together, so more strongly interacting binaries, you approach this sort of fundamental unit of luminosity, the so-called Planck luminosity. So namely, you radiate Planck mass in a Planck time. As you can see, the h bars cancel out, so it's something that can be realized by classical systems like binary black holes. So because of these extremely high luminosities in these systems, it allows for enough energy to be radiated that you can actually get a substantial gravitational wave memory effect. So unlike things like Mercury and the Sun in our solar system, or the double pulsar where the first evidence for gravitational waves was found, binary black holes are allowing you to probe this sort of interesting parameter space for the gravitational wave memory. Okay, so what then would LIGO actually measure? So I like to just have this little cartoon of two gravitational waves, one without memory in red and one with memory in blue. And if you had sort of an idealized LIGO detector, then the two arms would stretch and squeeze in the movie, but the initial and final states would be the same in the case without the memory. However, if you do have gravitational wave memory in this idealized LIGO, the final state of the detector would be slightly deformed. One arm would be longer and one arm would be shorter at position 5, as I've shown. So, as a matter of principle, this is straightforward to measure, but what's some sort of subtle about LIGO, trying to make a measurement of the memory, is that it doesn't really measure DC effects. It has a low frequency cutoff of 10 Hertz, so it only measures oscillations greater than 10 Hertz. So what one has to do to actually measure the gravitational wave memory effect are sort of two things. So the typical templates that LIGO uses are illustrated in the top left, where they actually don't include the memory effect. So you can see it's a zero mean waveform. It always oscillates around 0. Whereas the true waveform predicted by relativity is shown below, where there's a very small offset from 0. And there's kind of two data analysis strategies that one can use if you'd like to detect the memory effect. One is just do something like a hypothesis test. Say, is model A, the complete waveform, a better fit to the data than model B, the waveform without memory? Or what's a bit easier to illustrate is, imagine you use the incorrect waveform and you ask what's left over. Well, there would be some noise, but then there would also be what's in the top right, what I'm calling the gravitational memory waveform. So that is just a signal like, any of these very oscillatory signals on the left that you can search for. And what one can do is, just say, how loud is the signal? How much does it stand out above the noise? So you can compute a signal to noise ratio, which you can just think of as the significance of the detection in standard deviations. So if you do this exercise and compute the signal to noise for the kinds of masses and distances that the LIGO black holes have been detected, you'll see that all the yellow dots here, all these yellow stars, are below 1. So they're less than a 1 sigma significant detection. So, why am I then so confident that one can in principle measure the memory within the decade, this decade, in fact? And the answer is that you can do some more clever data analysis and look for the presence of the memory effect in the entire population of black holes and compare it to, say, a hypothesis that there's no memory effect in this population. So what's shown here is, one study that was done actually by a master's student, Oliver Boersma, who I supervised a few years ago. And what he showed, let's just focus on the red curve and then the associated error band, is that if you make many populations of binary black holes and you look at this sort of cumulative significance in sigma of memory effect in the data, how long does it take until you approach, say, 3 sigma significance? And it takes about 5 years of running the LIGO and Virgo detectors. And this is accounting for the fact that these detectors are not operational 100% of the time. They're only, in practice, running coincidentally half the time, roughly. So this is why I think it's actually quite promising that we'll be able to at least find statistical evidence for the memory effect through LIGO and Virgo measurements of binary black holes within this decade. Okay, I'll just mention as the last point, there's also plans to essentially build more powerful versions of LIGO and Virgo. The more powerful version of Virgo is called Einstein Telescope, which is a very sophisticated triangular detector, which hopefully will be operational in the 2030s. And then Cosmic Explorer is a plan in the US, which is basically sort of LIGO, but multiplied by 10, and with a lot of other tricks added. So what the curve in the top right shows is that the sensitivity of these detectors, so the green and pink curves versus that of LIGO, the blue curve, is factors of 10 better. So what this translates to in terms of the signal to noise is that, given what we know now about the population of binary black holes in our universe, these yellow stars, these observed events so far, we can expect signal to noises or detections that are close to 10 sigma significant detections of the memory effect in the next decade. So it's becoming quite interesting that we can actually hope to study the memory effect in some of these aspects of the infrared triangle, quite precisely. So to conclude, this is sort of the main points that I was making, that gravitational wave memory will likely be detected statistically in this decade, and then future detectors will, study it more precisely. So we really do have some access to one vertex of this infrared triangle. What I didn't discuss in the interest of time is that there's also memory effects related to these extensions of BMS algebra, and which have been called spin and center of mass memory effect. And these are sort of getting into the domain of where you might be able to find statistical evidence with the advanced detectors, but it's going to be much more challenging to try to observe them. But there's still the hope that even with these advanced detectors, we might learn something about some of these subleading soft theorems and the associated symmetries and conserved quantities. So I'll stop here.
Thanks a lot. So now the floor is open to discussion. And let me say again that Mark has to leave in a couple of minutes. So if you have questions for him, just unmute yourself. Okay, so maybe I start asking a question because I actually have one for on Mark's talk. So for the subleadings of graviton story, we have this situation that on the one hand you can look at holomorphic vector fields, and then you have your Zoro, or you have the full DFS2, and there's sort of this asymmetry which where the two choices are related, where Zoro and DFS2 are related by a shadow transform. In the leading soft or conformally soft Gravitino case, in recent work with Sabrina and my student Yorgo, we see something similar, that you have a choice, or in the conformal primary basis, it's sort of forced upon you because it's a kind of gauge choice, that there are two types of leading Gravitino fields. One at the boundary goes to a delta function and the other one to some meromorphic function. And so one gives equivalence with the soft theorem, while the other doesn't. And this is sort of mimics what is the situation in the subleadings of the graviton story. Do you see something in your spatial infinity analysis where some restriction on the fermionic, on the Gravitino, on the Golstino gives you a simplification, or?
But when you say the other does not, I mean, it leads to some other theorem, or?
Well, in one case you get a delta function, then you get on the nose the equivalence with the soft theorem. So, for example, Miguel and Alok showed this, that for DFS2 you get a one-to-one, but by this I meant a one-to-one equivalence versus one implies the other, but not the other way around. Okay. So I was wondering whether you had looked at holomorphic.
So we realized that we needed that to. I mean, for Jacobi, in fact, also for Lorentz invariance, it's needed. I mean, independently, we had an independent argument, but we did not explore the consequences in terms of soft theorems of that extra fermionic field and fermionic symmetry. Mm-hmm. So, I think that's an interesting question to try to understand the connection between the two approaches, but again, that needs to understand better how you go from spatial infinity to null infinity. But I have the feeling that everything can be translated. So it's just that the dictionary, the translation rules are complicated.
Glenn has a question.
Yes, I actually had a technical question, which was your chi field. In your notes, Mark, was so my question is, how does it go 1 over r or r to the power 0? Because you were saying 1 over r, and it looked to me that in the notes it was 1, which is r to the power 0.
Oh, yes, I was not, okay, I'm sorry if I wasn't clear. It's a gradient of chi that goes as 1 over r.
Yes.
Chi itself goes as, is order 1, so it's a function
Order
of
1.
only.
Okay. Very good, thank you.
Okay, more questions to any of the speakers and the panelists? Glenn, you still have a question, or is that's the hand just raised? So, okay. Okay, maybe I can ask David a quick question. So maybe I missed this, but your 5-year prospect for measuring the memory effect with 3 sigma, which year is that going to be?
Yeah, so there's a subtlety. So this was computed before there were some changes in LIGO's plans. So, you know, with the pandemic and then also with the proposed upgrades. So it looks more likely that it'll be the detectors will run for 2 years at their design sensitivity, and then they'll be down for, say, probably another year to 2 years to make these upgrades. And then once the upgrades are made, you know, there will be more detections. It'll happen faster. So probably another 2 years at this upgraded sensitivity. So that would, you know, put somewhere on the order of 2028, 2029. So it's, you know, end of the decade. But yeah, I'm revising some of these estimates now that there's, you know, been some changes in the plan for how the detectors are going to operate.
And you mentioned for spin memory or the center of mass, that's not clear. There's no clear, or is it clear how things have to be improved that can be measured? Is there a number of years that you can estimate, or is it totally unclear?
Yeah, so for spin memory, right, you can think of the standard memory as being generated by the energy flux, so the energy per solid angle. So this spin memory is generated by the angular momentum flux. And it actually turns out it's, at least for binary black holes, it's the orbital angular momentum of the binary as opposed to the spin that produces the spin memory. So, you know, not the best nomenclature, but it's the orbital angular momentum and essentially, you know, asymmetries in that. So that has been computed from binary black holes, and estimates have been made. I could, you know, show you quantitative things, but essentially, you know, the signal to noise for any individual event is going to be significantly less than 1. So it essentially relies upon the fact, are there enough events? And I think there's a good chance there are enough events, but I haven't actually done the quantitative calculation, you know, given what we now know about how many binary black holes there are in the universe. So
it may be within a decade or on a longer time scale. Sorry, I don't want to pin you down on some number,
yeah,
but just
no, that's, I mean, so these, you know, the current generation of detectors are funded and are going to continue to operate, but the next generation, you know, these are still being developed, so it's not guaranteed that they'll be funded. So if they are funded on the expected time scale, that would be, you know, one might be able to detect these, you know, at the end of the next decade. So somewhere in the 2030s, late 2030s, I think would be, you know, when it would happen. So that, unfortunately, we have to wait a while. I mean, there's also space-based gravitational wave detectors. If you've heard of the LISA experiment, that is another option where it's conceivable you might even be able to detect spin memory from a single event with LISA, but that's, you know, requires some optimistic estimates about how many supermassive black holes there are in the universe and how many are merging. So that's a bit uncertain since we don't actually have, you know, direct observations like we do with the LIGO and Virgo detectors of the stellar mass black holes.
I think Ala was next in the list.
I just want to follow up on that. So it's pleasing but puzzling that it's so easy to measure, because naively, you might think that it is suppressed by an extra factor of 1/r and dimensions of the, in units of the black hole radius, which would make it, and is it because you have to lose so much angular momentum for the merger, or why is it?
Yeah, so the effect that you measure still falls off like 1/r. So what's sort of interesting about the spin memory effect, right, is that it's a time integral of the strain, gravitational wave strain, or the shear, the CAV tensor. And it's specifically, it's, the part that's, a magnetic type or curl type field. So, LIGO and these other interferometers don't directly measure the time integral of the strain, but at least for binary black holes, if you have the spin memory effect, which is an offset of the time integral of the strain, there's some part of the waveform that has to produce it. And there's a way that you can pick out what this part must be. And that's what you would look for. So it's the measurement is more subtle than the standard memory effect, but it does look like it's possible. And there's something in the binary black hole waveform that you can identify as being associated with the spin memory effect.
And what about like the pulsar timing array, or are there other experiments out there that might measure memory in some form?
So pulsar timing arrays do look for the memory effect, and they've put upper limits. They're sensitive to gravitational waves of frequencies, between, say, 10 to the -9 and 10 to the -7 hertz. So, kind of year periods, because that's, how long their data sets are. Unfortunately, people have forecasted, how likely is it that the memory will be detected, and it looks not very promising. But, of course, there are always surprises in astrophysics, so I don't want to count it out. But, at least what's been published out suggests that pulsar timing is actually, less optimistic than LIGO and Virgo or this LISA interferometer in space that I mentioned.
Thank you.
Hello?
Yeah, I also had a question for David. So David, there is the tail to the memory, which is also universal. So why is that not something that is being looked at in LIGO, or is it?
Sorry, there's what part of the memory? I didn't.
It's the tail to the memory. So it's like the part of the radiation field which falls off as 1/t as you go at large time. And one can show from equations of motion that it's universal. It does only depends on the asymptotic moment of the scattering objects. So it doesn't depend on the details of the scattering, for example. So.
Okay, so yeah, I'm less familiar with this. So what is producing this 1/t effect?
So if in the case of gravity, there are there are two sources. One is the fact that the scattering objects are Coulomb dragged, so they're always accelerating. Mm-hmm. So they're always radiating, and there's a back reaction of the curved background on the emitted gravitational waves. So they both contribute and give you these tails. So they in the frequency space they go as log omega, and I think it has been shown by Ashok and his collaborators that they are universal. They don't depend on the details of the theory. So they are, and in the time space it goes 1/t. They only depend on the asymptotic moment of the scattering objects.
Okay, but this requires scattering, or this is something that would also occur for, these binary black holes are actually bound.
Yeah, it will occur even for it will also occur for like merger, for example. So you just, if you think of the black hole merger as kind of a scattering process, the two black holes come and then merge, then you would have the tail to the memory, which is universal.
Okay, and this isn't the tail from, if you have a curved black hole and you produce it, there are also these sort of, late time tails,
Yes.
In addition to quasi-normal ring.
Yeah.
Yeah.
So this tail doesn't depend on the spin of the black hole. It just depends on.
Okay. So it's a different kind of tail. So yeah, I guess my answer would be that I'm not completely familiar with this tail. So it's something that I'd be interested in looking into
Okay.
a little bit more to think about the detection prospects. But yeah, I'm personally not aware of anyone in the gravitational wave world who's looking at this. So yeah, it would be, if you could send me a reference or.
I think there were yeah, sure. I think there were known as hereditary effects in the old literature, maybe by Damour and Blanchet. You know, they had this paper, classical paper on the hereditary terms. And I think they were not called tails then, but I mean, they were present in their analysis.
Okay, so these also occur in post-Newtonian theory, you're saying these are during the
yeah, in post-Minkowskian as well as, yeah.
Okay,
yeah.
right. Okay, yeah, so I
Yes.
think, yeah, then let me correct what I'm saying. So for these post-Newtonian tails, there are people who, yeah, are essentially looking for the consistency of, you know, the gravitational waveforms with the predictions of these tails, because these kinds of tails appear at a specific post-Newtonian order, and you can, and I mean, it turns out if you write the frequency, you know, essentially, you know, these tails have, I guess, some thought in the post-Newtonian context, there's some logarithmic integral essentially, so they have some log term, but you know, there's a specific coefficient, which if I'm remembering correctly, is just pi, and you can essentially, you know, make a statistical test saying, is the coefficient of this expansion that you measure from the waveform, does it look like it's pi? And that is something that people in the LIGO and Virgo collaboration are looking into. So that's, you know, if you'd like a reference, I could point you to one for that.
Mm-hmm.
So I have also a question, I think more general about observations of this sort. How much of these observations should we really expect? How much of these features should we really expect to observe or measure, given that our universe is de Sitter, whereas on a large scale, whereas these effects are for asymptotically flat spacetimes?
Mm.
Yeah.
Yeah, so that's a good question. There's been some preliminary work done on this, but I mean, I think the basic idea is that, you know, in astrophysics, there's different scales. So the scale of these binaries is kilometer scales, basically, right? So then the gravitational waves, you know, propagate away from the system, you know, in the local environment as it would in flat space-time. And then the frequency of these waves is, right, hundreds of hertz, which is much, or the associated wavelength is a much shorter length scale than, you know, the curvature scale of de Sitter space. So it's, you know, a very good approximation to use geometric optics, for example, to treat the propagation of the waves after they're generated in what, you know, locally looks like an asymptotically flat region. And then if you work in this approximation, then, you know, essentially you just get the gravitational waves are redshifted and as the main effect that happens. So, you know, essentially since what LIGO measures is how fast does the memory ramp up, you know, that time scale associated with how quickly it ramps up would be redshifted, but it wouldn't say, you know, as far as my understanding of the literature, it wouldn't say erase the memory or make it not generated. You know, you'd still produce this memory effect, and the effect of the fact that we live in de Sitter just essentially changes how the waveform propagates from the source to the Earth where we're detecting it.
So will like the if I start thinking about subleading and sub-subleading memory effects, which are tinier and tinier, would you say the fact that we live in a de Sitter universe will become more and more important, just on a scale? Like if you want to measure spin memory, is the de Sitter effect higher than, like, if I want to measure the super translation memory?
I don't think so. I think my argument would still work that, you know, there's still some, at least with the spin memory, there's still some associated time scale with, you know, how this spin memory accumulates. And that's really what, you know, an interferometer like LIGO measures. So I think basically the same argument would hold, that it just, you know, would essentially redshift the waveform in the way that you'd expect.
Okay, thank you.
Alok, did you have another question, or is the hand?
Well, no, but okay, I can ask a question to Prahar. So Prahar, Kevin's talk yesterday, he had the effective action for the super translation modes, right? Which was also related to the square of the constant shear modes. I was wondering, you had any thoughts on that, with comparing with your effective action?
Yeah, as I said, you get the exact same action when I push it down to when I push it down to 4-dimensional bulk, and that's because of this special property that the shadow transform localizes for
it's exactly the
special
same. Sorry, yeah. I see. I missed that. So it's the same action. It's exactly the same action.
Yeah. So the shadow transform, even in 2 dimensions, the shadow transform does not localize for generic spin 2 fields, but it localizes for because the spin 2 field in 2 dimensions satisfies the CK constraint. So it turns out that if you do a shadow transform of a field that satisfies the CK constraint, then the shadow transform is local. So you end up getting a localized action in 2 dimensions for this special reason. And so if you take all of our results and just pull it down to 2D celestial CFTs, you'll reproduce all the actions that were given in the papers that I referred to in the first slide of my talk, including the one that Kevin derived using this boundary analysis.
Okay.
Miguel? Also, guys, you just yourself and talk.
It was for Mark, but I don't know if he still has some time or if he's leaving.
How long
You're muted. Huh?
Depends how long the question is. So go ahead.
No, because the other day, Arkan Hamed say some comments about n equals 8 supergravity, where there were some scalars with some nice soft structure that he was saying should be related somehow to asymptotic BMS because of supersymmetry. So I don't know if you had any comments on
for extended models that contain scalars, so n equal 4 and beyond.
Yes.
Well, we are at n equal 2 for the moment, so we have only spin 1, spin 3 half, and spin 2. But yeah, perhaps. But well, as you know, to understand these soft theorems for scalars, you have to dualize to 2 forms somehow, or to treat the dual versions. Okay, but these are just thoughts. We have not yet looked at that.
Okay, thank you.
Thank you. And well, I think now I apologize, but I have to leave. So well, thank you, and thank you.
Thanks a lot.
Thank you for the invitations again. Okay, bye-bye.
So I was wondering, Andy, if you wanted to I wanted to understand more this comment that you made about the localization in Mellon space. So for the current ward identity,
what I was really there were some other pertinent comments made about that, but just a statement that a single massive particle appears like a cloud, a non-localized object on the celestial sphere. I think that's a property of the momentum space wave function, and that the symplectic or the Klein-Gordon current itself will be a delta function. Somebody correct me if I'm wrong, but I think that's, but then Monica and Andrea both brought up in different ways the fact that, you know, bilocal interactions will have powers, which seems like a good thing. From the CCFT point of view, you know, these things are, we don't want ultra-local delta function interactions. It's nice that they have power laws.
Okay, I think at some point we did try to work in Mellon basis to kind of show that this you get a the ward identity becomes sort of the massive charge distribution becomes localized in Mellon space. I think we ran into all sorts of problems trying to show that. And for that reason, I think we just reached a conclusion that perhaps it wasn't really local.
Well, there's a more complicated question, which I think Monica or Mina or somebody could comment on, which is whether the current is, whether that has to do with interactions. I was just making a statement about the Klein-Gordon current, but whether the soft current generates it locally. Maybe one of them could comment on the latest on that.
Yeah, so I mean, we did I think probably a similar calculation to you, Prahar, and trying to show that the ward identity for, let's say, inserting a soft photon in the presence of massive particles localizes so that they're sort of, they look like, you know, ideally you would hope that it would look similar to the case of massless particles, that you bring the soft photon close to the other operators and they have 1/z minus W singularities or something. And the point is that no, it doesn't behave like a local current.
Even in Mellon space, it does not.
Yeah, even in Mellon space.
Oh, good.
Yeah.
Okay. That's okay. Good. Good. That is the.
And that was what I was saying is, well, you know, related to Andrea's comment, you can trace it back to the fact that, yeah, the Klein-Gordon product between two different massive wave functions is not a delta function.
So do you think there is a basis in which it would be local? In other words, do you think it's possible to think of a massive insertion as an integral of a local operator?
Okay, here's what I think. There's a separate question, which Mina and I are currently working on, which is you can just ask, okay, so you give up on the local stuff, right? But it sort of has to be true that at least the global ones work.
Yeah.
Otherwise, I think you derive some sort of contradiction. And that's kind of complicated, but we understand how to do that. Now you can ask the same question for you know, the infinite tower of symmetries associated to like the sub leading gravitons. And we're working this out, but my guess is that also probably works. And so then at the end of the day, my guess is that what you're going to want to use is you're going to want to use the Virasoro associated to that. Okay, so this requires a lot of work, and I can't. I just told you something.
Okay.
But I think that the massive ones, like as written right now, like doing the most naive thing, don't really behave like local operators. But maybe there's a way in which you sort of use a different symmetry group, slightly different one, and maybe then they'll behave more nicely. But
I see. I think the reason for my question was basically to essentially try and understand is it enough in this whole celestial CFT story? Is it enough to study correlation functions of local operators? Because if you're telling me that if I want to study massive particles, then it is possible to write a massive operator as some integral transform of a local operator, then I would say all we need to do is study local operators and then we're done. But if there are some other type of non-local operators in celestial CFTs which, you know, have no relation to local operators, then, you know, those should also be studied separately. Beyond just, so the OPE, for instance, in that case, would not be sufficient to fully understand the structure of CCFTs.
But Prahar, we don't know what the local operators are.
No, I know. I'm just wondering, even if we knew what they are, would they be enough?
Well, what does enough mean?
Could there be interesting and important to understand non-local operators which cannot be written as integrals of local operators? That's, I think, the question. And if there do exist such operators which are important to consider in CCFTs, then just studying local operators by itself would not fully reveal all the structure. And the only candidate for non-local operators that I can at the moment think of is massive. So that's why I asked my question. But I think Monica is telling me that it is possible. So at least as far as massive non-local operators are concerned, perhaps, studying OPEs, for instance, would be really enough. If we could do all the OPEs, that would be everything.
But what exactly, I heard a statement about well, let me first comment. I don't really understand why this why this issue doesn't already come up in just ordinary ADS3 CFT2. It seems like the mechanics of the calculation of boundary currents and
what I did in my talk. Yeah, I think that's actually a very interesting. I think one question was that if you try to do the similar type of construction in ADS, perhaps it'll reveal that it has to localize because the structure of the boundary in ADS is very different from flat space-time. So
no, I think it's almost exactly the same, right? Euclidean ADS3 CFT2, the transforms that you do to, write a local operator insert, it's all the same. That's where it all came. It's the same bulk to boundary.
I mean, shadow transforms do show up in ADS CFT as well, in the source and the responses. For instance, in other words, the source for a bulk field, which is locally related to a bulk field, is basically the response is the 1-point function of a boundary operator, right? And the source and the responses are precisely related by shadow transforms in ADS. So in fact, I think what should be possible to do, another way to perhaps try and derive these actions is to do the foliation and then use ADS D+1 CFTD. There, shadow transforms are very natural and they just sort of appear.
Right.
And I think they will reproduce the same actions that I wrote down.
Right. And by the same token, I would think that would give you some kind of current that would generate, if you have a boundary current algebra in ADS3, it seemed like the same sort of calculations should be that you use there to construct the current that obeys the right ward identity.
Yeah, the current that I wrote down. So actually, this action you can use it to construct the current as well, and indeed you get back the current that I defined using the shadow transform. So if I just give you this action and I tell you this action has a global U1 symmetry, so you would use the standard no other procedure to construct the current. And if you go through with that process and write down what the current is, you will end up with precisely the shadow transform of the soft operator. So actually that current is definitely hidden inside of this action, standard no other procedure.
So one thing in this context that's maybe a bit confusing is that the symmetry currents, so let's say the subleading soft graviton and the leading soft the supersymmetry current, they're all shadow transforms of primary operators. But on the other hand, the one-to-one equivalence between the soft theorem and the asymptotic symmetries comes from the other guys that are not the shadow transforms. So the diffs2 symmetry that Miguel and Alok talk about, or the analog statement for supersymmetry. It's a bit maybe counterintuitive if you think that those currents should be the local operators, which are all the shadow transform of primaries, and the equivalence, the one the bijective equivalence between the soft thermal asymptotic symmetries comes from the non-shadow primaries. I don't know.
I think that's a very good observation, and indeed it's very confusing to me as well. Because it looks like you have to shadow transform some subset of operators to define local operators, and for others you don't have to do it. And I don't know where to draw the line.
Well, I think that, you know, I guess I said something like this earlier, but, you know, if you're in a two-dimensional conformal field theory, if you're presented it in some way with an action or something, you can construct all kinds of operators that won't necessarily be mutually local. And then you have to do more work to figure out what is the good set of mutually local operators. And indeed, there might be more than one answer to that question. And if you haven't, sometimes you have an action and you construct a conformal field theory from it, there may be more than one way to do that. And it's clear that we're overcounting if we consider conformal primaries with arbitrary weight delta and their shadows and their light transforms. And personally, I was encouraged by the fact that the soft modes nicely fell into a W infinity multiplet if you light transform and play with each other very nicely. If you do a light transform, and so I would take that as a hint that maybe the light transform basis. And another hint for that is that they seem to be ubiquitously appearing in the conformal block decomposition of 4-point. But
can you remind me all the symmetry generators that appear in your W infinity do they come from the light transform of the conformal primaries that were originally defined, or
right? So in the paper with Mina, Monica, and Alfredo, we just worked out the commutation relations, and we got some rather long expressions, which we verified obeyed the Jacobi identity. So it is an algebra, and it was an expression in terms of the modes, and they were just ordinary Mellon primaries.
Okay.
But then when you do a light transform on one side, it seems the opposite side that Atul is doing it on, but okay. So if you do light transform on one side, this very complicated expression collapses down into a very simple algebra, which has been studied from many points of view, and it's clearly, I guess the first place this appears that I know about was Penrose's papers in the 60s on twistor theory. So it seems to be connected to. So that seemed like a hint that this might be good for a local basis. And indeed, and Atul showed, though he was in his talk, he was light transforming on the other side. I still can't figure out. And there's also probably two W algebras, one on the left and one on the right. I don't know how this all organizes, but that also eliminated the distributional nature of the scattering amplitudes. So that seems like an interesting thing to think about. Well, while I'm talking, I have a question for Prahar. So can you remind me again, why, if there are no infrared divergences above 4 dimensions, do we want to put a cutoff in, derive an action, and then remove it?
Yeah, no, my goal was to just try and understand more general features of whatever a celestial CFT should look like, as opposed to basically trying to remove out all the special properties that happens in 4D. So if you want to do that, you want to go to higher dimensions, then you have to introduce a cutoff. Otherwise, dynamics would be completely trivial. So, and we've seen, I think,
otherwise dynamics would be completely trivial.
Soft dynamics would be completely trivial. And since my goal was to try and understand these general features, the only way to do that would be to introduce the cutoff and then see. And I hope I was able to show in my talk that does yield some interesting structure. The fact that the field's action is local in terms of shadow transforms is not something that is at all obvious to me. Well, and that this also suggests, yeah, go on.
Well, two things. That the way you put it makes it sound like you're studying artifacts of the cutoff. And the second is there's still soft theorems in higher dimensions. So there has to be.
Yeah, so if you saw the action is not, yeah, the action is not exactly 0. There are 2 terms. One of them is proportional to the cutoff and the other one is not. So the term that's proportional to the cutoff completely goes away. And then the other term that's left over, that's a very trivial, that action is simply the soft mode coupled to the Goldstone mode. That's really it. It's very, very simple. So it's a 2-point function, but it's an off-diagonal 2-point function between the 2 fields. And that reproduces all the soft theorems completely. So it does reproduce every single soft theorem.
You can also keep big lambda finite and view the action as just resumming soft exchange. So it's just resumming to all orders the contribution to a scattering process between 0 and big lambda. So that if you were like computing an inclusive cross-section in higher dimensions, you don't have to, but you might want a better approximation to the process. And then this is what that action would contribute.
Very good.
Okay, but so we still think there should be a I mean, in the holographic paradigm, we still have to have a conformal, the dual still has to be a conformal field theory because there are no canonical spheres at null infinity. We only have a conformal. So the only thing that makes any sense is a conformal field. But aren't there, you're saying there's no sort of extra special boundary modes in such conformal field theories that we would?
No, there is. It's the same pseudo-Goldstone boson in any dimension. You just nonlinearly realize super translations or the local U1 transformations. It's just that you can't take the infrared cutoff to 0 in 4 dimensions. The action will blow up. You can take it to 0 in higher dimensions, and then you just have an effective action that calculates this portion of the scattering process.
But that's not a conformal field theory.
Yeah, in fact, in 4 dimensions, you must introduce a cutoff to have well-defined S matrix elements.
No,
you have to introduce it.
No, you can use coherent states.
No, but even those are defined with respect to a cutoff. And then you take the cutoff to 0 at the end of the day, but you really can't define coherent states either without introducing a cutoff.
Why not?
I mean, roughly speaking, the coherent states you should think of as some cloud of soft photons, and the soft photons, what you're calling soft, you're supposed to integrate over all 0 energy photons, which all are defined with respect to some cutoff.
You just have a pole in the frequency distribution.
At tree level, that's fine, but if you want to go beyond tree level to include all sorts of loop corrections, right, you will end up getting divergences, IR divergences in 4 dimensions, which you can only regulate if you introduce a cutoff.
Okay, I thought those all canceled for coherent states. Yeah.
Yeah, no, in the Coolidge-Faddeev dressing, if you didn't have a cutoff, you will cancel the 1 by omega pole for any omega which you don't want to do. So you must have a cutoff in the exponent in the Coolidge-Faddeev dressing. Otherwise, you would just kill the pole 1 by omega pole, which you do not want to do. You only want to kill the soft pole, not the pole for any frequency.
Yeah, I think you can't get around. You're forced to introduce a cutoff. Just like to define any quantum field theory, you have to introduce a UV cutoff. Even if it's UV complete, you have to introduce it, and then you can take it to 0 at the end of the day. But just to define various quantities, it has to be introduced.
So perhaps can I say something?
Would you say we have to do that in string theory? I don't think we have to introduce a UV cutoff and remove it. We just compute the.
I mean, string theory has a natural UV cutoff, the string length, so we don't have to do anything else. But the string length is the UV cutoff.
There are no UV divergences. There are also no IR divergences for.
But that's because of the string length, it's sort of a cutoff in the sense that it's a physical cutoff, which is given to us by the theory itself. But that's the reason there are no UV, because we don't have to integrate over length scales smaller than string length.
Can I say something? I mean, there's an issue with introducing hard cutoffs even in Coolidge-Faddeev, because then your S matrix won't be manifestly Lorentz invariant. I mean,
yes.
the way that, for example, Matthew Schwartz would do it with the soft collinear is to do dimensional regularization. So there you don't, there is not Lorentz invariance is not quite. So I mean, it's maybe just a technicality, but there is no hard cutoff you put in the frequency.
I'm not saying you have to introduce a cutoff which necessarily breaks Lorentz symmetry. I'm just saying the cutoff is needed just to define it. There are multiple ways to introduce it, depending on which set of symmetries you would like to preserve and make manifest.
But it's not entirely clear how to introduce dimensional regularization in the dressing formalism. Also, I mean, in soft collinear effective theory there is a way, but not in the Coolidge-Faddeev. We don't know how to do it using dimensional regularization.
I agree.
I had another more technical question. Somewhere you had a C with a C. Oh, you had a shadow with a shadow. And yeah, you said the thing was only local when you shadowed both fields, but since the shadow squares to 1, why wouldn't it also be local?
No, so the shadow squares to 1 only. Okay, that's a very good question. If I have 2 fields and I'm taking the so the 2 fields need to have dimensions which add up to D. Only in that case the shadow drops out.
Oh, because your fields.
By the way, that's also another thing that happens but that's special to 4 dimensions. So the fields C that I'm shadowing have dimension 1. So because 1 plus 1 is 2, so in 2 dimensions you would have a local action. But in higher dimensions, 1 plus 1 is not equal to D, so that particular action cannot localize at all.
1 plus 1 is still 2?
1 plus 1 is 2, but it's not D. Yeah.
I see. I had a question for Laura, if she's here. Maybe she's not. Yeah. So you said you computed the OPEs. So does this the P3 halves, 3 halves, does that is that ultra local? It just has contact OPEs. Is that what?
The P, the curly P, the OP of the curly P.
Yeah.
Yeah, right. So the bracket. You want the P with which one? Which was with?
You were calling it curly P. It's a primary with dimension 3 halves, 3 halves. And
exactly.
You said you computed all the OPEs of everything on your.
Yeah. So we computed the OP of this guy with from the algebra. So we have the you know, we have the OP of the curly P with say the curly J, and then you can also rewrite this OP, so you can get the OP, for instance, with curly P and the stress tensor, and then you find that it's, you know, the OP that the 3/2 should satisfy.
But is it, I'm wondering if it's ultra local, is it always delta functions? Does it only have contact interactions?
Which OP do you want to look at? Which bracket or which the P?
All of them, or any of them?
So the let me see. If there are some delta you're asking if there are delta functions. No, is I mean the OP of curly P with the stress tensor is the usual OP with 1/, you know, Z minus W squared times 3/2. And,
right. Because the stress tensor is a shadow, right?
Yeah. The stress tensor, yeah, the stress tensor is the shadow of the delta equal to 0, indeed.
But you would have contact OPs with the Mellon primaries, right?
Right. Yeah, exactly. Yeah, because you would inverse shadow this thing, so they would give delta functions.
Yeah.
You say the stress tensor will have contact OPs, or the derivative of the stress tensor?
Well, so in ordinary CFT, we would throw out something with only we only talk about operators. We would say it corresponded to a null state or something, or we would throw out anything with only contact OPEs. But if we start shadowing, we can turn things with contact OPEs into power law OPEs. And so if we shadow everything and consider everything in its, I don't know, so there should be, I guess we would hope that there would be some set of operators, a smaller set of operators. Since P3/3 is a descendant of something else, we might think we're not losing any information by throwing it out. It's a descendant of a Mellon primary. But if we start shadowing things, then it has non-trivial OPs at finite separations. So I guess we need some rules about when we shadow and when we don't, and which things we keep.
Yes, indeed.
Maybe a comment here. So I think this super momentum and super angular momentum are precisely these, I mean, the weights match exactly the generalized primaries at the bottom of the celestial diamond. So those are primary descendant of the asymptotic symmetry generators, but in the memory diamond, not in the Goldstone diamond.
Yeah.
Wait, say that again, slower.
So the operators that Laura talked about, the 3/2 for the HH bar, or 3,0 in delta and J, those are precisely the weights of the, so in this case, it's the bottom corner operator in the leading soft graviton diamond.
Yeah.
But in the memory diamond, because it's related to the hard modes, to the actual soft charges. And the other one, the super angular momentum, should be also the bottom corner operator for the subleading soft graviton. So the weights match exactly those that we call generalized conformal primaries, because they are not, the 4D spin is not equal to the 2D spin. And you get, when you insert them into correlation function, you get delta function. That's precisely what you want, because you want to land on the soft term. So the operators at the bottom of the diamond are the soft operators that Banerjee and company talk about. And then the soft charges that you get by taking the super translation function and the super rotation vector field, and you convolute that with the asymptotic symmetry generators, which have delta equals 1 for the leading soft graviton, and delta equals 0 or 2 for the subleading. This gives an interpretation of the superposition vector field and a supertranslation parameter as being the Green's function for going from the soft operator at the bottom of the diamond up to the asymptotic symmetry generators. And I think the ones that Laura was talking about are the ones that are at the bottom of the diamond, so the soft operators that Banerjee is talking about.
The difference here is that the things we have are Vera-Zero primaries. They are, they are not quasi-primaries. They are full.
And are these primary descendants the ones that you brought up in the tables? Or? So
they are all primaries, primary field, Vera-Zero primary field, thanks to this curly derivative that I've introduced, well, that we didn't introduce actually. Glenn, Miguel also have looked at that. So the descent, if you want, in the sense that indeed if you want this curly P, is the second descendant of the is the first descendant of the supertranslation current, which himself descend from the soft operator, the leading soft operator.
Yeah,
but the way we constructed with this vacuum structure and this curly derivative makes them make all these objects to be Vera-Zero primary fields, all of them. So in particular, we don't have in the OPE of, say, P with T, we don't have anomalies. They are,
Laura, can I ask a question? So this older work of Stefan and Thomas on the looking at the extended BMS algebra in the celestial CFT. So they also didn't get the anomaly, but
no. Okay, so I was talking about the fact that you have, in their paper, for instance, the supertranslation current has an OPE with the stress tensor that has a 1 over z to the 4 times. You see, I was talking about that.
I thought Stefan and Thomas' paper did not have the 1 by z to the 4. I mean, that maybe I'm wrong. I mean,
you're thinking about T with T.
No. Even in P with T, at least in the paper, what I remember that from the conformal double soft theorem, they got the closed extended BMS algebra, and that was part of the confusion, at least, that somehow they were not getting this 1 by z to the 4 term even with the old stress tensor, without this the new terms that you have now. The extra term they did not have, as far as I remember, the z to the 4 term.
I think they do because they constructed. So I'm really talking about the OPE of the super translation.
Yes, only super translation and super rotation. Yes.
Exactly. So in their OPE, they have a central. I mean, they have an anomaly because they constructed from taking the first descendant of the delta equal 1 Mellin primary. So they take a conformally soft limit and then take a derivative. And then it's the OPE of a descendant of weight 3/2.
Okay.
You see, and there you get it in one of the two. I think it's in P with T
or T bar
and T bar. Yeah, probably. Yeah, exactly.
But then how is it that they got the closed algebra without the 2 cocycles? Sorry, do you know? I mean, the commutator algebra they got did not have the anomaly. They just wrote a closed algebra, right?
Yeah, I don't know how did they. Oh, okay, how they did derive the algebra.
I don't know if one of them is there, we can ask them. But yeah, I think they had a closed algebra, right, in that paper from the OPE.
I'm not quite sure that yeah, if it was if they derived that from the OPE. I know at some point they have this, so they compute the OPEs from the conformally sublimits of the amplitudes, right? And there is the next section where they start from the BMS algebra without any, without anything, and then they build up this 3/2 guy actually by starting with the zero mode of the super translation current, take some commutators, use the OPE that they have between the stress tensor and a generic, say, primary Mellin representative, and then I think what they do is they build up the OPE of this 3/2. So yeah,
I see. Okay.
I think the starting point was the
algebra.
section was the algebra. Yeah.
Okay.
It was this way around.
Prahar, can you say anything about what you would expect in D equals 3, like bulk D equals 3? You're muted, by the way.
Bulk D equals 3 is something that I really want to look at next. So in particular, what is, okay, good. So there's many things to say here, I think. So the first thing I want to point out is that I think this phase factor that I talked about is really significant. I mean, I think it's significant even in 4 dimensions, but it's definitely significant in 3. It's established to be significant in 3 dimensions. I think let's put it that way. So let me give you an example. So there's this paper by Shiraz where he basically derives S matrices in Chern-Simons matter theories. And there's no photon, as we know, 3 dimensions, we won't really have a photon, but there is a Chern-Simons field, so you can have photons travel inside loops. So you do get this soft exchange sort of diagrams, but you don't have external photons. So these soft modes will play a role, and there's perhaps some sort of effective action that you could write down to determine this. Now, the way he wrote down this, so he wrote down an exact S matrix to all orders in the perturbative expansion. And the way he wrote down was to simply solve Schwinger-Dyson equations. So he just found solutions. And in particular, he found this very interesting. He found 2 solutions to the Schwinger-Dyson equations. So he had 2 different sets of S matrices for the same theory. The first S matrix was crossing symmetric, but not unitary. And the second S matrix was unitary, but not crossing symmetric. And there was no S matrix that was both unitary and crossing symmetric. So the question is, can we really see what's going on if I try to, by the way, just to be clear, S matrices, and it was in flat space-time. So it was precisely the context that we're interested in. So in this example, I think what's happening is that we have this amplitude, which is the full amplitude, which factorizes into a soft piece and a hard piece. And the soft piece has a phase. And the phase factor has this very special structure where it only couples to in particles or out particles. So it has it sort of really distinguishes between in and out state. And in particular, that phase is not crossing symmetric. So if I take an in particle and move it to being out particle, the phase will completely change. So indeed, because of this IR divergent phase, the full amplitude, I don't think is crossing symmetric, but it, of course, is unitary because it's just the overlap of states. So I think, and I would like to explore this more, I think the S matrix that Shiraz found, which was unitary but not crossing symmetric, is the full S matrix. But then the hard amplitude, after you extract out this phase and throw it away, that hard amplitude will now be crossing symmetric, but it won't be unitary because it's it can no longer be written as an overlap of states. So I think those are the 2 S matrices that he was finding. And I really do think that if you try and do this analysis in 3D, there'll be some interesting results. And this phase will play an important role. I do have an action that reproduces this phase as well, but It's just something I wrote down by hand, which works, but I have absolutely no understanding of where that's coming from and why that should be the correct action. Yeah, I think that's all.
But what's the puzzle here? So I thought that, I mean, usually in non-exotic situations, you can show that the S matrix is crossing symmetric, right? It's not a fundamental principle, is it, that the S matrix has to be crossing symmetric?
No, it's not a fundamental principle, and it typically isn't because of the IR divergent phase. As I say, the phase is not crossing symmetric.
Okay, so he wrote down the S matrix. He solved the problem. So
no, but he didn't understand it in terms of these IR divergent. He just solved Schwinger-Dyson equations.
Right.
But, and he worked out exactly what the breaking. So when you do crossing symmetry, he basically got the amplitude that he expected multiplied by a phase, and the phase was basically you can understand it as some Wilson loop, some correlation functions of some Wilson loop in Chern-Simons theory. And the structure is something that he just worked out. All of these were just exact formulas written down by solving equations, really. What I'd like to understand is if this sort of Wilson loop type phase that he was getting is precisely coming from the fact that the way you extract this phase is by evaluating Wilson loops. As I showed, the operator insertions UI, they're essentially Wilson loops. So which I got from symmetry, so just by looking at symmetries of the problem. So it does look that there's a lot of similar structure, that some insertions of Wilson loops is the result, is what we need to do to extract the crossing non-invariant phase. I would like to make this precise. I mean, it looks very inviting and sort of feels like this has to be the right answer, but none of this has been really worked out.
And what about the action? Is it because you said, in the higher dimensions, it's non-local, D equals 4, it's local, and so.
Oh, D equals 3, it will. That's a good point. I actually didn't even bother trying to understand what the structure is in D equal to 3. It's probably still going to be non-local. Because the shadow transform has special properties, because these weights have the operators that I'm taking a shadow transform off, they have weight 1. And as I very cleverly mentioned before, 1 + 1 is 2. So I think it's this special thing only happens in 2 dimensions, but because it's not equal to 1, I think you'll still have these non-local stuff going on in 3D. But we might have to change the structure of the action, because one of the fundamental assumptions in D greater than 4 was that sort of the low energy physics of photons is governed by the Maxwell action, which is not true in 3 dimensions, because the low energy physics there is governed by the Chern-Simons action. So I suspect probably it's just going to be a completely different type of action as well. The one I wrote down probably will not be the right answer in any case.
What happens to these boundary terms if you add topological terms like R wedge R, R wedge R wedge R, F wedge?
Yeah, we have some conjecture. I think Dan, well, so you might ask how to generalize this with magnetic charges, because then, so for instance, you can add in the non-abelian case, you can add Wess-Zumino type terms in 2 dimensions. And so similarly in higher even dimensions, you can add similar higher dimensional WZ terms, and we don't know. I think it's very interesting to add them and just ask what happens. By the way, I think for magnetic charges, we do have to include them to describe magnetic charges in 2 dimensions. And in order to reproduce your magnetic soft theorem, you have to include another coupling, which is precisely basically the coupling of a B mu field, a Kalb-Ramond field. You basically write down a B mu coupling in 2 dimensions to the action that I wrote down, and that reproduces for you the magnetic soft theorem and magnetic IR divergences that you have. That was not, I think it's interesting, but it was too much for a talk, but it's in the paper.
The one that came out yesterday or something?
Yeah, yesterday for you, I think.
Yeah, that's why it's important that there are 2 scalars in the description system, is so that you can add the B mu field. And what that does is basically to alter the spectrum in the 2D boson, just in the same way that turning on a theta term gives you the Witten effect and the Dionic spectrum. So you can sort of see it just because the theta term is a derivative of the Chern-Simons term. So you get a Chern-Simons term on scry, and then you try to integrate that along the null direction, and it basically turns into a
boundary Weston-Lino term. Yeah, it can be exactly derived from just the theta term in the bulk. And as Dan said, because it's a total derivative, it doesn't contribute to the 2-point functions or the action, but it does modify the spectrum of the theory.
Hi. I just wanted to make a comment regarding what this need of introducing or not a cutoff when you do string theory amplitudes. And as Andy said, I think it's indeed true that you don't really need to introduce a cutoff, for example, at the loop level, for example. So for example, if you compute, the annulus diagram, so the planar diagram in type 1 superstring, and the Moebius diagram also in the same theory, then the fact that you have to choose SO32 as a gauge group cancels exactly these divergences without the need of having to introduce a cutoff.
Yeah, so but I think what's happening in string theory is that there is a natural cutoff, which is the string length.
But no, you integrate from all the way from 0 to infinity, and these cancellations just go away. I mean, okay, you can argue that you have to maybe put like an epsilon cutoff in the energy, and then you see that you have 1/epsilon, 1/epsilon with the opposite sign, and they cancel out in the planar and the Moebius strip diagram. But that's not, I mean, it's just that you could say that it's just, some principal value prescription, and then the cancellation happens anyway. And you don't really need a cutoff, at least in this example.
That might be true, but I think it depends on also what question you're. So, I mean, the only example that comes to mind.
Well,
but
if you ask a physical question like the scattering between two states that satisfies all the conservation laws, then there'll be no infrared divergences. Now, you seem to be agreeing that the infrared divergences will cancel at the end of the day. And whether or not, but you're saying that you needed at intermediate stages of the calculation, but that seems to, as Francisco was saying in the analogy, that seems to depend on how you set up the calculation. So it seems to be a little bit of a philosophical point of whether you need an infrared cutoff or not. There are ways of doing calculations in which the cancellation of infrared divergence is manifest at every step. So you don't need a cutoff.
Well, I think
that's how I would say it. I don't.
In 4 dimensions, maybe Dan has a comment.
Go ahead.
No, I didn't. I was just asking because in greater than 4 dimensions, I think you can completely describe everything without ever having to introduce a cutoff, and I'm perfectly happy with that.
Well, I would just say that there's 2 different cutoffs that you can discuss. Yeah. One is a hard infrared cutoff. The other is a cutoff that you put in between hard and soft particles. That is like a detector sensitivity question and is something which you deal with in any dimension, right? So if you have an experiment that can't detect part of the Hilbert space, whenever you don't have access to part of the Hilbert space, you trace over that part of the Hilbert space. And so, if you had a 6-dimensional particle detector that can't detect photons below some wavelength, you still trace out that part of the Hilbert space, and you still have this big lambda in the formula, and that's what the action is computing. You don't need a hard IR cutoff on the lower end, but there's still a place for this other scale, and that scale you still have in 4 dimensions because when you make these dressings, you're trying to fix the extreme IR piece of the state, but you have to sort of say where the IR piece of the state stops and UV part of the state begins, and that scale is still there. So I don't know like a prescription that completely does away with that hard soft cutoff, even the body of Coolidge. basis.
Well, I think if you go to a conformal primary basis and you dress with Goldstone bosons that either incoming or outgoing, that there's no divergences.
So would you be dressing them with the exactly delta equal to 1 Goldstone modes or some small neighbors?
That's not really true. Wait, is that true? No, that is true. Yeah. That's what we claimed in our paper with Nima. So first we of course it all looks a little different and maybe simpler on a conformal basis, but we showed that the exclusive S matrix factorized into a hard and a soft part where all the cutoff dependence was in the conformally soft part. And then we argued that that part just simply wasn't there if you had dressings. It was just canceled.
I mean, that paper has formulas with logarithms involving a single scale, which don't make sense, right? Like the argument of the logarithm is naturally a ratio of 2 different scales. That's the way that sort of always arises. And I think the other scale is usually this hard soft cutoff.
Right.
But if you use the hard soft collinear factorization, I mean, we don't need a hard cutoff, but if you define the hard S matrix using the hard soft collinear factorization, then, I mean, that hard S matrix is IR finite, right? The one that Schwartz defines, for example.
Sorry, I want to address Dan's assertion that what we wrote didn't make sense. It does make sense because if you look at the 2 sides of the equation, the operators that are inserted have different dimensions. So when you do a transformation to a conformal basis, you have omega to the delta minus 1. So those operators have a dimension. And so on the 2 sides of those equations, we have operators with different dimensions. And because we're shifting the thing in the exponential, and the log of the cutoff exactly makes those, the exponential of the log of the cutoff exactly makes that, is exactly what's needed. But I agree, it's a subtle point which confused us when we were writing it, but I believe it's correct.
So you don't, I thought in that paper you had quantities that looked like log of pi.pj. How do we make sense of that sort of?
Well, it's the same thing. You know, just the dimensions of the 2 sides of the equation have to match.
Right, but if you're taking log of something, that's whatever is inside the argument has to be dimensionless, no matter what you're matching it to on the other side.
No, you can write, it's an exponential of the log. So e to the alpha log pi.pj is pi.pj to the alpha. And that has some dimension. And so the dimensions on both sides of the equation have to.
Okay.
Sorry, are those states when you do this integral and you don't cut off the dressing in the UV piece of the spectrum, they're still supposed to be, you don't introduce new like UV divergences from that piece?
Well, right. So these are not energy eigenstates. And that's why the Fedheev and Kulish ran into this tension between, you know, they were working in traditional formalism where you would like to have energy eigenstates, but they wanted a soft pole and they had a soft dressing, and there's a natural sort of conformally invariant choice for the soft dressing, but those have infinite energy. And they certainly didn't want to consider that, so they put these, so they consider a whole infinite class. There's nothing to organize their dressings. So it's a highly overcomplete basis. But if you want to work on a conformal primary basis, there's a unique dressing, that conformal primary dressing that has the right pole and is a conformal primary, and it works out to essentially be equivalent to the Goldstone boson. Now, as far as UV divergences, we're assuming that all of these amplitudes are exponentially suppressed at high, you know, that we're doing the Mellon transform of something which is exponentially suppressed at high energy, because we're assuming that quantum gravity is soft at, so, you know, so we just assume that these things exist and converge, and then we analyze their properties. I mean, this is a weird fact about, right, Mellon amplitudes, which I guess Tom and Stefan, you know, like they computed the string Mellon amplitudes, and you just have the power of alpha prime out front. There's no alpha prime expansion. Yeah, it's weird.
But I mean, would you say that those are the states you should also use in higher dimensions, even when you don't have an infrared divergence?
You know, I'm waiting for somebody else to explain higher dimensions to me. It looks like, yeah, I don't know. I guess. Well, I mean, I'm looking forward to reading your paper, but I don't. Doesn't seem like you would want to have dressed. Why would you want to have dressed states if there isn't a divergence?
As Dan pointed, you might want to have dress states if you're talking about inclusive quantities. So
okay, but why do we want to? I mean, you know, if we're, you know, okay, if we're going to compare to experiments, we need to talk about inclusive quantities, like you know, David Nichols was just explaining to us. We, you know, that there's a IR cutoff, and we don't, you know, in the memory effect, and so that. But if we're just trying to understand, you know, for the program of trying to understand holographic duality and infrared symmetries or asymptotic symmetries, why do we want to think about inclusive stuff? It's not quantum mechanics if we're tracing out over. I mean, the idea is that, you know, there should be an S matrix, an idea which I think was unhappily abandoned, right? That there should be an S matrix in quantum field theory, and that was thought to be in trouble because of infrared divergences, and we still don't know. You know, Hernan was talking about this, and I guess we'll hear. We still don't know what the situation is in you know, in QCD or in non-abelian gauge theory, but you know, the symmetries that we're talking about are symmetries of the S matrix, and If we don't have an S matrix, there's nothing to talk about. But it seems like there is an S matrix. Well, I think there is. I mean, there's plenty of things I'm still confused about, but I think there is an S matrix, and I think there should be one in higher dimensions too. And yeah.
I mean,
and
sorry, can I ask something?
Yeah.
But there is still a puzzle in higher dimension that if we just follow the original Coolidge-Faddeev derivation, that we just look at the interaction potential and see whether it goes to zero at late times. And the fact that if you have any soft particles and the phases do not decay, that is dimension independent. So if you follow that procedure, then in any dimension, the states will get dressed, because the dressing of the Coolidge-Faddeev was, it was just coming from the analysis of the interaction potential at late times.
Yeah. So I'm glad you raised it. I don't agree with Faddeev-Coolidge in that point. There's no need to dress states in general. So, for example, at an accelerator, we don't collide dressed protons or electrons. We don't like, after we throw in our particles, that we don't like throw in a cloud of soft radiation that corresponds to.
Right.
And what happens is that, you scatter two particles like this, and if they aren't dressed, so you can solve the incoming constraints for incoming hard particles without dressing them. And any good physical theory should explain to us, what to do in that situation. What happens? Well, we have to satisfy all the conservation laws. And what happens is that when they scatter like this, the Cherenkov radiation, there's a dot of soft radiation that goes up to Scri. If you don't dress it on Scri minus, there's a dot of radiation that appears on Scri plus. So in a real experiment with in and out particles, the out particles will carry dressing with them. The in particles won't, but there'll be sort of shadows, not these shadow transform we're talking about, but light shadows associated with it. So there's no argument like Faddeev-Coolidge were making that all physical states must carry clouds of soft particles with them. And for that matter, those Faddeev-Coolidge papers were really a long time ago. And I don't think they understood what null infinity was. And they were dressing massive particles.
Yes.
And so even if you put a cloud of soft stuff around a massive particle, which goes to time like infinity, the soft stuff will go out to null infinity, and you'll end up with an undressed particle at late retarded times anyway. So, yeah. So I don't think in 4 dimensions or in higher dimensions, we need to only scatter in or out dressed particles. Just if we don't satisfy all the conservation laws, the S matrix will vanish.
Right.
But it seems super interesting to think about higher dimensions, just like taking lessons from string theory. People thought about 10 dimensions, they thought about 4, people actually mostly just thought about 10 dimensions. And then it seems that there was a different story in every dimension. And it was weaving all those stories together that gave us sort of unified picture of all the string theories. And I'd imagine here that there's some very interesting story to be told, which I guess there's been some progress on. I mean, there must be some story because there's soft theorems, and I guess yeah, I guess. Well, I need to digest the new results.
I mean, there is a qualitative difference, at least in even dimension, right? That the mode conjugate to the soft news is I mean, the linear in R mode is really U independent in 6 dimensions. It's not the radiation is in the R to the 0 component of the shear. So I think there is something qualitatively distinct.
I mean, in some sense, it's even nicer than 4 dimensions because there's a clear separation between the Coulombic modes and the radiative modes,
exactly,
which does not happen in 4 dimensions.
You know, another way one could think about this, there's another way of thinking about all this is there certainly will be an operator product expansion. There's collinear divergences in any dimension, right? So it seems like there would be an operator product expansion. And it seems like that operator product expansion is going to have the Euler beta function in it again, because that Euler beta function just comes from, you know, when you do the Mellin transform and you go to 2 other conformal primaries, you have to integrate over all possible ways to divide the energy between the 2 states in the energy basis. And that's basically T to the delta, 1 minus T to the delta prime or something.
Right.
So it seems like you get the beta function again, and then that tells you that you'll have poles in the operator product expansion. And then that will give you soft modes, and those soft modes would seem to be special boundary modes in higher dimensions in the same way they are. But that must be what you were trying to derive, no?
Yeah, I mean, that's, I think, the point of this action is that, but we don't, so in this action, we wrote down just the exactly soft modes. I suppose in the conformally, in the Mellin basis, these are the modes that have delta equal to 1. But if you would like to, we'd like to write down an OPE for arbitrary delta, and this action definitely will not do the job for that.
The delta equals 1 mode, I see. So, but that would still, but maybe in higher dimensions, the action starts at lower. Yeah, maybe in higher dimensions, the interesting stuff happens at lower delta.
Yeah.
What is delta also equals 1 also a?
Delta will always be 1 for the soft mode because that's.
Sorry. Go ahead.
I was just saying delta will be 1 in any dimension because that just comes from the fact that you're picking out the 1 over omega pole. Which now doesn't lie on the principal series, and that's another confusion that I have.
But it doesn't have to, right? I mean, it's an accident for dimension that it just that the leading soft photon and graviton lie on the principal series, have this degeneracy between the positive and negative helicity, because all the other, the subleadings of graviton, the leadings of gravitino, they don't lie there, and they're not symmetric between positive and negative helicity. So I think generically they probably shouldn't lie in the principal series.
Maybe I can ask a more general question. Is there any extrapolate dictionary for massive field in the celestial, in the conformal primary basis? I mean, like in ATS CFT, we have a good extrapolate dictionary for the bulk fields. Is there something like that? I mean, the usual way we won't have, right? It will exponentially decay if you go to null infinity, if you take a massive field. But we expect something nice to happen when we go to celestial, I mean, conformal primary basis. Or
there is some sort of extrapolate dictionary and you have sort of, you take integrals over light rays and they select out for you. So you have a U integral with some power that contains delta.
Even for massive fields.
Sorry, I was talking massless.
Yeah, no, massless. Yeah, I'm saying for massive, which is the.
Thank you. Any more questions, comments, confusions?
I was just gonna add. So Andy, you think your paper where you derive the OPE, the celestial OPE for gluons and gravitons, that can be general. That should be. I think Dan and I discussed this as well some time back. That should be generalizable to higher dimensions as well.
Well, I think there's an even simpler paper by Monica and Mina. I would try to.
Okay.
I would try to recent one, right? Yeah. Yeah. And the calculations. I mean, we did all the OPs in that paper. If you just want to start off at, you can, the calculation that Steve Berger and Taylor did is not that hard. I see. So maybe that's what I'm. Yeah. What was worrying me was that what you had looks too simple. But as you say, you're not trying to get all the soft modes.
Yeah, and in fact,
there might be more.
There's definitely more. Definitely. I mean, for instance, we don't talk about the stress tensor at all, or the subleading soft gravity.
Yeah, you said that. You said that, right? So, yeah, you said that, right?
But I actually think I may even have a way to include these additional delta modes for arbitrary delta. And I think it goes back to trying to work out what the phase of this infrared divergence is. That phase factor has a very interesting sort of structure that, and I totally don't understand right now, but if you really wanted to extract, as I said, I just wrote down an action, and the action you need to introduce additional fields which have an extra delta dependence. And I don't know I'm calling it delta, but it doesn't necessarily have anything to do with the delta in celestial CFT, but the structure looks the delta is basically, well, it's of the form 1 plus I nu, so that's very suggestive that I should really think of it as the same. D over 2 plus I nu, sorry. So it does have the same structure as a scaling dimension. And so you have this whole new set of fields that one needs to introduce simply to reproduce the phase factor in the IR divergence. And I was wondering if once I introduce this action and I just write it down, could it then be used to extract OPEs of arbitrary deltas? I haven't gotten anywhere near there, though. I just wrote down an action, just that'll work, but I don't really have any other calculations that go beyond that. So I really do think this phase is important. It's not something that can be just thrown under the rug.
Oh, yeah.
So for instance, I definitely wouldn't claim that we have a soft action that reproduces the full soft dynamics of the theory because we haven't yet explained this phase and where that's coming from. So
yeah. Wait, but it is incorporating the magnetic stuff.
We've incorporated the magnetic stuff. As I said, that's you just add a B-mu coupling to the action. And not just magnetic charges, but well, it's probably they're closely related, but magnetic charges also the addition of the theta term, all of those have been incorporated as well. And they're both simply related to adding a B-mu term to the action, which then couples to the magnetic charges.
You don't need the B-mu term for just magnetic charges with no theta term.
With no theta,
yeah. For that, it's just a coupling to the topological current in the 2D compact boson. So it's just like a source for the other U1 in the compact boson. But then if you want to change the spectrum with the theta term, then you need the Kalb-Raman field.
Yes, that's correct. I said it incorrectly. So in other words, the operators UY that I wrote down, which those I wrote down by assuming that all the particles are electrically charged. So they just transform under electric gauge transformations. But of course, if they're dionic and they also have carrying magnetic charges, you have to include additional interaction terms, which additional terms in the operator UI, which capture the magnetic charge of the particle. So we have done that and then included that in the action. So then that can give you the soft factor and soft IR divergences, everything for magnetic charges. And then on top of all of this, you can also add a theta term, which will be the B-mu interaction. Yeah, sorry, that's the correct structure.
There's this interesting issue in that context of what happens when you have your lattice, charged lattice becomes critical and you get extra null.
Yes, so I think I'll tell you this
FU2 or something, or you get other gauge.
This paper was delayed by I think 2 months because we spent 2 months trying to properly understand the relationship between E and M duality in 4 dimensions and T duality in the 2D model, and we didn't actually resolve it. I don't think we've fully understood it yet. So I mean, in order to answer your question about the cell-dual radius, I would really have to be clear about how the duality works and what the relationship is, and I definitely wouldn't say that I fully understand it. So we've written something. Part of what we understand is in the paper, but it's definitely not the full story.
But the cartoon would be that electromagnetic duality exchanges basically the 2 gauge U1 symmetries in the bulk, the same way that T duality exchanges the 2 U1 momentum symmetries in the compact boson.
Right. This question might be simpler in 2-2 signature. You don't have to worry about things getting complexified.
That would be interesting because, in fact, things getting complexified is precisely what was confusing us for this entire story. Okay. That's an interesting idea. That might be a good thing to explore.
Any more comments or questions? Or shall we reserve some energy for tomorrow?
Sounds good. Thank you.
Perfect. Thanks
Thank you
a
very
lot
much.
for the discussion, and thanks a lot for all the speakers and panelists for their talks.
Thank you. Thank you.
Everybody
Thank you.
participating.